Resources Management. Tom has served as a manager with the field enforcement team for more than 12 years, leading rule drafting efforts, reviewing well construction, and plugging operations, including remedial cementing procedures, coordinating inspection and also enforcement activity. Currently, he is reviewing new classes of cement and cement remediation options for compliance with Ohio's code and administrative rules. Tom has worked at ODNR for more than 25 years. He was a mineral resource inspector for 10 years and spent 5 years as a conservation coordinator. Tom received a bachelor's degree from Kent State University in 1997. Take it from here, Tom.
Thank you, Todd, and welcome everyone, and thank you for taking the time to be with us today. We have a great panel of speakers today to discuss changes in cement, and that panel consists of our first speaker today, James Heathman. James Heathman is currently a consultant with over 35 years of global industry experience, primarily in oil and gas well cementing. This experience encompasses operations, R&D, and management roles for major integrated service companies and both independent and major operating companies. He holds a BS and an MS degree in petroleum engineering from Louisiana Tech University and an MBA from Oklahoma State University. He is an author of over 36 publications and an equal number of patents, is a lifetime member of the SPE and an Emirates member of API, and currently serving as the chairman of API's Subcommittee 10 that is responsible for developing and maintenance of industry standards on oil and gas well cementing, equipment, and processing. Then we will have Jason Weingarten. Jason is the technical advisor for Next Tier Completion Solutions cementing production line. He began his career in 2008 as a cementing and stimulation field engineer with Schlumberger in Midland, Texas. He moved to the Appalachian Basin with Superior Well Service in Blacklick, PA in 2011, and spent the next 7 years leading their cementing engineering group, working in the Marcellus and Utica shale plays. He returned to Midland, Texas in 2018, following C&J Energy acquisitions of Otex Pumping to lead the Permian Cement engineering team, and was moved into the current role in Houston, Texas in 2021. After Next Year was formed from the merger of C&J Energy and Keene Group. Unfortunately, Craig Enos wasn't able to make it today, but presenting will be Bill Hergerth, and he is a major marketing manager, cement, for oil and gas in Northeast United States for Holcim. In 1990, Bill graduated from Northwood University, Midland, Michigan, with a dual major in management and marketing. In 1991, Bill started his career in the cement industry as a terminal operator in Milwaukee, Wisconsin. As his career progressed, he took on increasing management responsibilities in terminal operations throughout the United States. William gained experience in all facets of cement supply chains, including vessel, barge, rail, and truck. In addition to operational responsibility, he was an active member in developing safety, environment, and community outreach for Holcim in the local level. In 2003, he was presented with the Maritime Person of the Year by the Propeller Club of the United States, Port of Nashville, for this role in the development of a scholarship program for Nashville, Tennessee students. In 2005, he moved back to Western Pennsylvania to take on his current role as Holcim re-entered the cement market. As the Marcellus Utica play developed, William took an active role in industry trade groups to support the responsible development of the emerging shale industry. In his personal life, Bill is a proud husband and father of 2 sons. He followed his true passion for community by coaching baseball from Little League to his last position as the Harper Valley Middle School coach in Nashville, Tennessee, until his move back to Pennsylvania in 2005. He enjoys golf, gardening, cooking, eating, and is focused on family, friends, and community. And the final speaker will be myself, Tom Hill. Thank you.
Okay, good afternoon, everyone. James Heathman here. Going to go over a very high-level information this afternoon with on behalf of the American Petroleum Institute on specifically what the specification 10A means. There's a bit of misunderstanding about what it actually means for cement, so I'm going to take piggybacking here a little bit this afternoon. I'm going to take a minute to clarify some of that. Then we're going to get into the what the differences are between the new 2 classifications that we introduced, which is K and L, and why they were created. And also there's still ongoing work going on in subcommittee 10 regarding the use of additional limestone. And I expect that work to be going for quite some time, but we do have some very active things going on at the moment.
James, can you turn on your video, please?
Let's see, video. Start video. Sorry, I thought that was on. Okay. Can you see my happy face now?
Yes.
All right. Amy, if you would advance my slide. Thank you. Just a little bit of warning clarity now around what Spec 10 is all about. It was created over 50 years ago for quality control purposes, and it gives both chemical and performance specifications. What you have to realize is that these specifications were created back in a time when the understanding of cement reaction chemistry was not as good as it is now. Manufacturing controls and QC methods were paled in comparison to what manufacturers have now with SEM and some other methods they use. And of course, the additive chemistry in the oil and gas part of it, the additives that the service companies use now are many, many times more advanced than what they were. I'll go as far to say that most service companies can take virtually any cement in the world, and if they have enough time to work with it, they can make pretty much any cement do whatever they want to do. Whereas even as little as 25 years ago, that was not possible. So it was created as a manufacturing specification for quality control a long time ago. It's not an end user specification, although it is sometimes misapplied as an end user specification. Somebody will say, well, this tender, this contract must have cement that has a Spec 10A monogram on it. There's not that many of those around anymore, even though cement, excuse me, a lot of cement manufacturers will make cement in accordance to API specifications. So that means that yes, the cement was made to the exacting specifications that API has, but because they're not in the monogram program, they may or may not have the audited quality control system in place that would be required if they got audited under the API monogram program. Okay, Amy, I'm still having slide advancements. Thank you. This is not to blow everybody up with a bunch of numbers and death by PowerPoint. What I wanted to show for you here for the United States and most of North America, you only have 4 cements that are currently available in the API classification system, which is A, C, G, and H. And even G is predominantly on the West Coast and in Canada. Permian Basin, middle of the country, places that we're most accustomed to is more the usage is A and C primarily, and then H is used for the high temperature applications. And what I wanted to I just point out a couple of random things there, but you can see there's very little difference in these specifications. The way the cement is manufactured. When you get down into the high sulfate grade resistance, you'll see a bit more performance specifications laid in on some of these, primarily dealing with the sulfate resistance, which is dealing with cracking if the cement is exposed to sulfate formation waters later in its life. Slide, please. The performance specifications set out under Spec 10A are very simple. We only consider the thickening time, compressive strength, and free fluid of the cement as it is manufactured in the mill. This is not a reflection on or should not be used as a guide for what is used in an actual well in the field, because this is a very strict performance specification to say that, yes, this cement does meet these specifications. Now, once it leaves the mill, the end users will change it up with additives as needed. And these are very straightforward. They meet certain thickening time and compressive strength minimum requirements to meet the monogram requirements, or the Spec 10A monogram requirements. But that can be modified very easily with any of these by simply changing something as simple as the water ratio, the mixing water content. You can change those considerably. Next slide, please. Okay, so K&L, what does it really mean? These were introduced back in 2019 for those that have not haven't pulled up the Spec 10A, which everybody has access to it through the api.org website. It's for purchase, and the specification simply states for Class K, it concentrates on the silica flowers, and typically it's meant to be more of a normal cement. The Class L is concentrates more on the pozzolanic and fly ash materials. Now notice that while these cements or while these specifications only call out a few things, it does not exclude anything. So I can have limestone, which seems is the big topic of conversation. I can have limestone in either K or L. It doesn't matter. And realize also that classes A and C already have limestone in them, interground limestone. G and H are the only two that do not, as it currently stands. And this is copied word for word right out of the spec. And I believe these slides will be available for anybody that needs to see them later. So the synopsis of the K&L, they concentrate on either intergrinding or blending Portland cement with silica and pozzolanic materials. Now realize too that the service companies have been blending cement with all of these materials since day one for various purposes. This is only, the K&L is only applicable to what comes out of the manufacturing plants. And there's another little bit of a confusion that has been coming up periodically, is that the L in Class L denotes limestone, similar to what the ASTM classification does with the 1L, which does denote limestone. Class L does not address limestone directly. It doesn't exclude it, so it can be there or not. So just because somebody has Class L in a recipe that they submit you, it does not mean that it does have limestone in it. So that's one thing you want to keep in mind about the L. That was probably not a good choice of classification letters, but when we came up with that, we just didn't think about that L could be confused with limestone. Next slide. So what you really have with K&L, it's actually a reflection of years of already existing practice. So so-called limestone and many sources of pozzolanic materials have been used in many decades for oil and gas. I've even seen volcanic ash used as a pozzolanic material over in the Philippines. Very good material while it lasted. You also have a lot of natural poz. You get out in New Mexico, Arizona, there's some mines out there that have natural sources of pozzolanic materials, zeolites, and then things of that nature. And then we also have the calcined shales, which are manufactured products, much like a cement clinker is made and then ground. So there's lots of different ways of doing this. It's been around for a long time. K&L is not bringing anything really new to the market. It's a reflection of what's already been practiced for a long time. So all the cement blends that end users use they're driven by technical needs, economics, and logistics, pure and simple. The only two classes that right now in the API classification system that do not have limestone specifically included is classes G and H, which have always been historically used for the high performance, high temperature, heavyweight slurries. There is work currently underway in the API Task Group 2, Work Group 3, investigating low concentrations of limestone that can either be interground or blended by the manufacturers. The blending is not, there's really no big deal because that's been done for a long time. A lot of times ground up limestone is used for low circulation materials. So this is nothing new in that respect, but the interground is new. It's going to be, right now we're looking at a limit of 5%. So this will allow manufacturers to include limestone in these two cements, performance allowing. The performance testing is underway right now, but that will be going forward. And I don't know, but depending on the timing, I don't know if that will be as an addendum to the Spec 10A or it will be in the next edition. That's work to be decided. And that concluded my material, and now we're moving on to Jason with next year.
Andrew, are you able to pass control over to me? Okay, perfect. Thank you. All right, everybody. I wanted to, let's see, is it going? Let me do this. So a few topics I want to cover today. So I want to talk about the changing market conditions and the supply chain struggles we've seen. So since COVID hit, so we've gone through this drastic.
Jason, I'm sorry to interrupt, but could you turn up your mic just a little bit?
Let's see, how do
Or come closer to it.
Can you hear me now?
Yes,
Okay, much better. Somehow it switched to the wrong microphone. It switched from my webcam to the laptop microphone. All right. So today I want to talk about the market conditions. We've seen the market change drastically in the last two and a half years since COVID hit in early 2020. We've watched the oil and gas, we watched the rig count drop, recover, and we're seeing tighter market conditions now than we've ever really seen when it comes to cementing materials. From those changing market conditions, we've seen quite a few supply chain struggles, and I'll talk about the historic amount of cements that we've used and the efficiency gains we've seen on drilling rigs. And then I'm going to talk about some of the alternative materials we have used in the past and some of the ones that are being used currently, and we'll go through some of the lab results, particularly on the limestone cements. As James mentioned in the previous presentation, there has been a lot of discussion on limestone cements, and I've got some end-use lab results to present here, comparing the use of the limestone cements versus the more standard either API or ASTM type 1 class A kind of class A, class C kind of cements. There it is. So from 2020 through today, we've seen a drastic change in rig count. So we had a huge crash. So you can see this is beginning of 2020 through, well, I think I updated this at the right around Thanksgiving time, but we haven't seen much of a change in the last 6 weeks. But from 2020, we started to see the market soften a little bit at the beginning, and then COVID hit, and OPEC turned on opened up the taps, and we saw the oil price crash and we saw rig count crash. Permian showed the biggest crunch, along with the rest of the majority oil producing basins here in the US. Williston, South Texas, West Texas, Mid-Con. These are the ones that were primarily affected. So the demand for hydrocarbons back then was not as high as it is today. Now that we've come out of lockdown, and people are trying to get back out there, travel demand is exceptionally high. Demand for goods is exceptionally high. The demand for hydrocarbons is probably higher today than it was going into COVID. The rig count has recovered, but you'll see in the next slide that the efficiency gains that we saw with these drilling rigs, with the way these rigs are able to drill, we're now using more cement today. So this is month over month. So if you look, this is January 2020 through October of 2022, the total amount of cement, and this is just a percentage scale for scale. But you can see that we saw the big dip in cement consumed through the summer of 2020. We see that we were, by summer of 2021, just on the cement consumption for well construction in the Permian. By summer of 2021, we had recovered to the levels that we were seeing before COVID. And now we're, in 2022, we were anywhere from, typically anywhere from 20 to 40% above the amount of cement we were consuming for well construction in the Permian pre-COVID. So when COVID hit, these drilling rigs, a lot of them shut down. And what these operators and these rigs were forced to do is they were forced to find ways to become more efficient. Those efficiency gains that they saw, so those efficiency gains that were realized during COVID and during the recovery period are still there today. These rigs can drill much more quickly, and they can get a lot more lateral feet drilled, and they can drill a well much more, but with the skidding rigs and offline cementing and all the other technological advances we've seen, these rigs are able to get a lot more lateral feet and more wells drilled with fewer rigs actually being used. So that explains why we've seen a recovery to the so if we go back one slide, we can see that we're back at around the same number of rigs. Total rig counts right around 700 again, but especially for the Permian is pretty similar, but we're using 30% more cement now because of these efficiencies we've seen. Another one for comparison, this one was a little bit more insulated from the COVID crash because it was more of a natural gas basin, and the natural gas demand wasn't quite as affected as the oil demand was. Now, there was still a dip during COVID, but you could see in that first slide that the rig count for Appalachia was pretty constant. It really didn't dip. It didn't see the huge crunch that the oil basins did. But you still see going into today, we're right around that same level we were, with maybe a tiny bit above here at the end of 2022. We're just starting to peak back above the cement consumption we saw pre-COVID. So along with that increase in cement consumption, we've seen a lot of different things going on in the cement industry. So we need to stretch the cement that we've got, because we don't have as much as, we no longer have wide open access to well cement like we used to. When COVID hit, these cement manufacturing plants, they looked at the oil and gas industry and said, well, they've crashed. We need to turn to make something. So a lot of these oil and gas, these cement plants that were manufacturing well cement, pivoted and started manufacturing construction cement. So the well cement, the amount of well cement that was available for us to use dropped. There are not as many plants right now making well cement as there were at the beginning of 2020. So we need to find ways to stretch this cement, because we're competing for that construction cement as well. We're competing against the construction industry. We're competing against infrastructure. We're competing against a lot of different people who are trying to pull and use that same cement we are. So conventional pozzolans are an easy way to stretch cement. These have been used for a long time: fly ash, silica fume, and you can get pretty far. You can go 60 to 65% by total weight and still see reasonable compressive strength and reasonable cement durability. It's probably once you get up to that 70 or so percent where you start to really see a breakover in compressive strength, because you don't have enough cement to really kick off that reaction. There are also alternative pozzolans, natural pozzolans like perlite and diatomaceous earth. These have been around for decades as well. These are going to be more regionally restricted. These are going to be mined. So these are going to be mined products. So wherever you've got a deposit of these products, they're going to be, wherever you're within reasonable trucking or rail distance is where you can use these. Calcined shales, as James mentioned in the previous product, this has got a long history of use with Martin Marietta Lightweight, which used to be Texas, TXI Lightweight it's been around for decades as well. It is a proven pozzolan that has good performance in oil well applications. Now, there are also inert fillers, so calcium carbonate or limestone. This one's the big one. This one's the one that's really coming into play nowadays with type 1L cements and Holcim's Class L cement. We're substituting now, the construction industry is substituting in type 1L 10 to 15% by weight of cement with limestone. And Bill from Holcim will talk more about this and why they're doing it. But we are seeing a lot more base cements that we're seeing a lot more base cements that have more and more calcium carbonate or limestone blended in. Now, the oil and gas industry has used calcium carbonate for decades and decades and decades as a filler for different purposes, whether it's to stretch cement or whether it's for properties to optimize completion and lateral. We've used calcium carbonate in cement for decades for taking up space and filling space and extending cement. There we go. So what else can we use? So we can use construction cements. So type 1 and type 1, 2, type 3, these have a long history of use in oil well cementing. There is a lot of construction demand, but it is seasonal. So it eases up on us. There is more type 1, 2, and type 3 available in the wintertime, especially in the cold climates, the Rockies, the Northeast, places like this. Texas has a pretty solidly, year-round construction season. It'll shut down here and there for some of the cold weather snaps, but there isn't a big lull in demand for construction cement in Texas like there is in other places. Now, Bill will talk about this as well, but type 1, 2, and type 3 are going away. So we're starting to see some of these limestone blended construction cements. So type 1L is replacing a lot of these type 1, 2, and type 3 Portland cements in many markets. So it is in use already in well construction in some areas. We are using it in the state. We as Next Year are currently using it in the state of Virginia. And I know, we have not used it in the state of Texas, but I know there are other operators and cement companies that have used Type 1L in the state of Texas with temporary approval as well, with temporary approval from the Railroad Commission. API Class L cement. Bill will talk more about this, but this is a limestone blended cement from Holcim. Now, this slide might be a little confusing, and this is kind of where James mentioned. So API Class L cements, as James said, it's cement blended with a pozzolan, but it doesn't exclude the use of limestone. So the Holcim Class L is a blend of cement, pozzolan, and limestone. There is a significant portion of limestone added for extension, for Portland reduction purposes. Again, the Martin Marietta lightweight is another commercially available lightweight Class L or cement that could be considered a Class L that would fall under the Class L blanket. Less common, these advanced sealing materials, so epoxy resins and non-consolidating plugging materials. These are pretty niche products. The resins you're going to use for casing leaks and really small volume jobs. And the non-consolidating plugging materials, this is another niche product that might be used when you've got when you've got some sort of really challenging well to abandon or something like this, and you've got a very high pressure zone you're trying to shut off, and normal Portland cement won't fix it. It's more of a niche product that I'm not really going to go into a lot of detail about today. So we've talked a lot about limestone, and Bill will go into why limestone is such a big thing, but I've got some comparison results from an end use purpose. So in the Northeast, Holcim has replaced Class A with Class L cement. So I've got 3 different comparison slurries here, and you guys will be able to see these results after the fact. But the take home here is Class L, at least for as far as thickening time, compressive strength, and slurry stability from a free fluid standpoint goes, they're very comparable. There is no winner or loser. They're very comparable when it comes to compressive strength, thickening time, and slurry stability. In fact, because of the smaller particle size required to get the reactivity back up to get the compressive strength out of the Class L, we very often see better slurry stability and lower free fluid out of the Class L when compared to the Class A. Now, talking about Type 1L. So we talked about Type 1L as well. So I've got some comparison results here showing Type 1L in different applications. So this is for a typical Northeast. I guess this is for some typical Northeast shallow surface intermediate and some shallow vertical conventional production strings where we might use Type 1 in let's say the state of Virginia. So all these are, all of your neat cements are mixed at 15.6 here for the surface and intermediate, and we've got a 50-50. I'm sorry, that's the third one, is a 50-50 pause Type 1 or Type 1L mixed at 14.2. Again, we don't see a huge difference in performance out of any of these 3. In fact, the Type 1L has the best compressive strength performance out of any of the slurries that are shown here. Really the only difference when it comes, in my eyes, when it comes to an end user's, from my perspective, the only real difference in these 3 is the additional reactivity you get out of the Type 1L compared to the Class A. And you see the same additional reactivity, the shorter thickening time, faster compressive strength development out of the Type 1L or the Type 1 when compared to the Class A. And again, the take home here is both the Type 1 and Type 1L, because of their finer particle size and their higher reactivity, they're both better at building compressive strength and better at maintaining stability and showing lower free fluid than the Class A would be in a lot of applications. So one thing that if it comes, if we need to at the end of this, and there are questions about it, we have also evaluated for use in the Permian a Mexican a construction cement from Mexico. Now this is a Holcim product that we have evaluated here. It is a Mexican CPC 40R. Now, this is a blended cement. So CPC in Mexico is similar to like a Type 1L or a Type 1P here in the US. It is a blended cement, and the 40R is really just a, that is equivalent to high early compressive strength is what that means. So it's very similar in compressive strength development to a Class C, but it is very similar in composition to a Type 1L. So this one is in that 10 to 15% limestone range. So for comparison, we threw some testing together between, to compare our typical surface casing slurries that are Texas Railroad Commission compliant between the Class C and the imported Mexican limestone blended cement. And again, we saw very, very similar results between these. There is no clear winner or loser here. Either one, at least in the eyes of Railroad Commission, when it comes to compressive strength requirement, free fluid requirement, either one would pass. Either one of these would meet the requirements with flying colors in our typical applications. In fact, again, due to the reduced grain, due to the reduced particle size of the limestone blended cement, we see a big increase in compressive strength with the blended cement compared to the straight Portland cement, the straight Class C Portland cement that we typically use in the Permian, especially on those tail slurries. You could see the second tail slurry, you've got 1200 PSI in 72 hours versus almost over 1800 PSI in 72 hours out of the blended cement. Same thing for the 14.8 neat density slurry. Class C with 2% calcium chloride, you're looking at 2300 PSI in 72 hours versus over 3000 out of the blended cement in 72 hours. So again, really the take home here is that from an end user's perspective, from the testing we do, from a service company's perspective, we don't see much difference between the performance coming out of a typical pure Portland cement, whether it's an API or an ASTM, C150 Portland cement, versus the limestone blended cements, whether it's Holcim's Class L or a Type 1L or even the Mexican limestone blended cement that we've evaluated. So to wrap everything up, the market is changing rapidly. We've got to make sure we're in front of it. The energy demand is not going away, so we have to make sure that we're ready to react as these market conditions change. Construction demand is going to go up, it's going to go down. We're going to be in these binds all the time. Cement plants have issues. Cement plants are finite. There aren't, there have been, there really are no big plans for increasing drastically the amount of Portland cement that's being produced in the U.S. right now. You don't see cement companies investing tons and tons in building new plants. So we're kind of restricted with what we've got. We've got to find ways around the limitations we have, and blending limestone, blending alternative pozzolans, doing these different things is the easiest way to do it. So before anything's implemented, obviously we need to have a thorough round of testing and thorough vetting before we just throw anything, before we go pump anything into a well. But I think especially the limestone, based on the data I've shown here, the comparison testing that shows this limestone and even the other pozzolans, they show adequate properties for oil well use. I mean, compressive strength, especially in these limestone blends, is comparable and adequate. Slurry stability is often improved by the addition of these limestones and these other pozzolans. So we've got a lot of options, and we just need to make sure that we're able to use them so we can stay out in front of the rapidly changing market conditions. And with that, I'm going to turn it over to Mr. Herguth.
Good afternoon, everyone. Why low CO2 cements? Amy, can you do the slides for me? I can't get them. And one more time. The key thing for me is takeaways. I just want to go over the API ASTM definitions again. This is really important in the field. ASTM cements are always going to be designated by a type 1-2, type 1L, type 3, type 5. And the API cements always be designated with a class L, class A, class H, as you've seen earlier in the presentation. They're both standards organizations. They're both utilizing oil well work, but that terminology of type and class is critical. And to understand the difference will go a long way in helping everyone understand exactly what cement you're talking about. So again, ASTM is type and API is class. Next slide, please. As an overview, the cement production reached in the United States was 90 million metric tons in 2020. There was 4.1 billion metric tons produced in the world. One of the key things about lowering our CO2 impact is that the cement industry contributes around 8% of all CO2 emissions released globally. And just as a note, the oil and gas industry in the US represents less than 1% of the total cement demand in producing in the United States. And another key takeaway is 1 metric ton of cement produced equals 1 metric ton of CO2 released into the environment. Next slide, please. If you can just take a look at some of these news articles that were released showing concerns of CO2 being released by cement manufacturers and concrete manufacturers by utilizing cement in the United States. These different news articles are not favorable to cement manufacturing. And it's one of the main drivers for us is to lower our CO2 releasing during the manufacturing cement. Can you go to the next slide, please? So also policy starting to change. And I wanted to highlight this slide showing that currently in the United States, we do not have carbon taxes on the cement manufactured based on CO2 release. However, just north of the border in British Columbia, as an example, there's a $27 charge per ton as a carbon tax on every ton produced in Canada. And if you scroll down to the bottom, you can see the impact of this in Sweden. They're charging the governments are enforcing $139 carbon tax on every ton produced. So this can show you the financial implications of CO2 as we go forward with policy. So as Holcim, we're trying to lead to lower our CO2 for multiple reasons, mainly for the environment, but these are the impacts in our financial sense. Next slide, please. LafargeHolcim, or Holcim, has been trying to lead to lower our CO2 released in the manufacture of cement, but it's not just Holcim that's doing this, it's the industry doing this. And this chart right here is a LafargeHolcim slide, but it shows you, if you look at the top left, in the early 90s, we were releasing about 800 kilograms of CO2 per manufactured ton of cement. And if you look down on the bottom, you'll see that the chart go over to 2022. That 550 kilograms that released per ton of cement is based on the 1L launch that Holcim launched in early January 2021 at the majority of our plants. And that's where we believe right now as a global entity that our current releases for CO2. Our 2030 target at Holcim is 475 kilograms per ton. And I'll go in a couple slides, I'll go over, explain a little bit how we're doing that. And then in 2050, our target is to be a net zero producer of CO2 in the manufacture of cement. Next slide, please. To explain how we're manufacturing the API Class L cements, I wanted to go through a chart of our plant and manufacturing facilities, how we manufacture cement, to show, and then I'll show you at the end of the next slides exactly more detail. But to the top left, we obviously pull limestone from the ground in a quarry, we truck it over to a belt, we take it to our first primary crushers. This is pretty standard for any cement plant in the world. So the primary crusher breaks down the limestone in the size of about the size of a softball. It goes to a secondary crusher and it breaks it down to about a 1 or 2 inch size. And there's fines and different sizes, but about 1 or 2 inches is the largest size that goes through. And then we take that over to a proportioning system where we add sand and clay in there with the limestone itself. It's properly proportioned. It gets sent over to the grinding mill, if you're following along on the chart here. And that brings everything to a very homogeneous, around 1 to 2 inches, about 1 inch. It kind of looks just like basic cement. It's not reactive, but it looks very similar to cement. And then it takes it up to the preheating tower. Once that material or the raw feed gets into the preheater, it's starting to heat up right there at the very beginning of the tower. And then as it goes down, it's heating up even more. And it's starting to become somewhat homogeneous. And then it hits the front of the kiln. That's temperatures around 2,700 degrees Fahrenheit where the chemical reaction happens. And at the end of that kiln, that's when the clinker is produced for the final product, clinker, the cement clinker with the chemical reaction, and it moves over to the clinker cooler. That process takes not a long time. It lasts maybe, less than an hour most of the time to get through the clinker cooler. But if you can see that chart, all the designs of cement plants today are trying to maintain the heat, lower our costs, but also lower CO2. But the heat itself off that heat exchange in the clinker cooler is taken back to the preheater tower, which you can see on the schematic. And then as the clinker is cooled, it goes through the process. And this box is highlighted, so I'm gonna show this on the next slide, but this is where the intergrinding of the cement, the gypsum, the pozzolans, the limestone happens. It's very, very efficient. It's all proportioned and it's interground to make a homogeneous product that's consistent. Oil well cement has to be consistent. Our goals at Wholesome are obviously to make a very consistent cement, regardless of which cement we manufacture. But that's where the intergrinding happens. And then it's moved over to the cement storage silos, and that could be a truck direct to a customer, or we could load it onto rail cars at that time or barges and then move it to the end terminals directly to the end users. And that's how you manufacture cement. That's okay. Please, next slide. So we're going to dial in the last of that red box. So how is it made? So this is really the key component of the manufacture of cement is the kilns. Like I said, it brings it up to 2,700 degrees Fahrenheit. We utilize coal, natural gas, alternative fuels, literally anything we can that has, that we can fire these kilns with, we'll use as long as it doesn't impact performance of the cement. Obviously, we do this to reduce waste to landfills. The significant BTU content can't be underestimated. We draw a lot of power to produce this product. All of us do in the industry. And as you can see on the left, the CO2 is released. It comes right out of the top, goes right up our stacks. And that's basically 1 ton of cement equals 1 ton of CO2 release. Next slide, please. This slide right here is I'm going to let you look at this for a little bit, but if you focus on the left side, this 0.9 cement or clinker factor, that's a direct relationship to CO2 release. So currently, if we look at the 0.9, that's like 1990 and all the way up to 2021, when we changed the 1Ls, where you see the 0.9 factor, and it scrolls down to the 0.85 factor, the 0.8 factor, and even below to 0.6. Right now, Wholesome is in the middle phase. We have a partial replacement of OPC with branded blended cements like 1L, API class L for oil and gas. And below that, you see the corresponding ASTM C595. And then I also see there in the middle is the class L oil well cement. That's kind of where we're at today. And then as we go forward to get to our 2030 targets, 2050 targets, we'll be converting to more branded blended cements and more performance cements. And as an example of those, if you look down below, the ASTM C1157's performance cements, these are some of the names that we have. We have competitors, I'm sure, will be doing something similar. And as Jason mentioned earlier, there's natural pozzolans, fly ash, slag, some of our branded or some products we have like EcoPlanet, Solidia. These are all different markets, not oil and gas, but different segments like block, brick. Every different segment we have, we are targeting to lower CO2. Next slide, please. I guess that's me and for me, Tom. So but that's it for me. I will be open for any questions. But thank you very much for your time.
Tom, I passed you the mouse. If you want to try to see if we can get that.
Sure. Thank you. So with all these changes coming to cement manufacturing, where does that leave the regulators and the regulated community? In Ohio, our administrative code for well construction requires that all the cements that are placed in a well bore have to be API 10A specification for cement materials, or ASTM C150 and C150M cement. In addition, we have performance standards for those cement. West Virginia, Pennsylvania, and Texas have similar requirements, and reviewing other states' rules and regulate laws, some states are just based on performance standards with cement. For plugging, at least in Ohio, if a pozzolanic cement is used, the content cannot exceed 50% by volume. In our plugging rule, we did not include ASTM C150 or C150M cements, and ASTM C595, which would be the type 1L cements, were not included in the rule at the time of drafting. You go to the next slide, please. Okay.
Did you want this slide or the one before it?
One before, please. So the division was informed that most, if not all, current suppliers of API Class A cement and Type 1 cement would be ceasing production of those cements and replacing it with the API Class L or the C595 Type 1L cement. Our code allows the chief to approve in writing cements that may be used for plugging and construction that there are not performance standards issued for. So in March, our chief approved a memorandum approving the ASTM C15 and C150M cements, that's your type 1 and 2. And later in September of 2022, the chief issued a memorandum allowing for type 1L cement to be used in plugging of orphan wells. In September also, the chief issued a memorandum approving cement manufactured to meet ASTM C595 type 1L cement to be used by industry to plug wells. In addition to that, the memorandum applied conditions for the use of Class L cement in well construction and well plugging. Next slide, please. We mailed out letters to all our registered owner and registered well pluggers, informing them of the changes. In those changes, we included that they must notify our inspectors 24 hours prior to the cement being utilized, provide them with mill test data, performance data for them to review to make sure they meet the Ohio Administrative Code. We set a limit for blended cements. The limestone and pozzolanic material in those cements cannot exceed 50% by volume. And our rule requires an operator leave a well exposed after it's been plugged for a minimum of 3 days. We stipulated that we can extend that for the inspectors to be able to assess the performance of the Class L and Type 1L in plugging operations. Next slide, please. So a lot of the questions that came up when we were informed of these changes, what is going to be the long-term integrity of the cement sheath when subjected to downhole environments? How much performance variability is there going to be depending on the percent of limestone, especially in the type 1Ls? How resistant is this cement going to be to temperature during the operational life of the well? And neither of the wells have published performance data. So that was the requirement that they have to provide that to us before it is utilized for our review. Go ahead, next slide. So the division took the steps of, we collected samples of type 1L. We sent that to an independent lab. We had it tested for wellbore conditions at 60 degrees and 113 degrees. We picked shallow temperatures of a conductor or surface casing, and we picked an average temperature of a deep intermediate casing to test the cement to. We're also tracking the type 1L and Class L performance data submitted by the industry. We're starting to build our own cement tables for that, especially the different blends of cement. The division is participating in a cement research discussion group with multiple states. They include Pennsylvania and West Virginia. We've kept a very open line of communication with cement contractors and cement manufacturers, especially for supply issues with cements and any other changes. We also had our Ohio Technical Advisory Committee complete a study on type 1L cement and had them make recommendations. And that wraps up with the steps the state of Ohio has taken to this point. Open it up for questions and discussions.
Any questions? Use the raise your hand button at the bottom of your screen. Todd, I don't see any questions right now from the audience.
I see a question, so I'll allow them to talk. Susie, you have to allow yourself to be unmuted and then you will be able to ask your question.
Okay, I had just had a question. I know you said there were some cement coming in from different countries. Is there a consistency or a QA/QC issue with cement coming in from other countries?
And I can take this one. Any imported cement that Holcim brings in from the world goes through everything is performance checked. Everything is tested. It has to meet all the standards that we have in the United States. So that the answer to your question is any cement that Holcim brings into the United States has to meet our expectations and performance requirements, as well as the state's or API or ASTM specifications.
And just to add to that, the Mexican product that we did evaluate was manufactured at a Holcim facility in Mexico. So, you know, Holcim's one of the major players in the cement manufacturing industry worldwide. I wouldn't think that there's going to be that much of a difference in their quality control from one country to another just because of their ISO qualifications and registrations. They've got to maintain a certain level of quality control across all their plants in order to maintain those registrations and certifications. So from a major cement manufacturer like that to bring a Lafarge Holcim product from Mexico or Canada or something like this into the US, I would not think that there's any significant problem with quality control just because of the manufacturer. Now I think the major, all the major cement manufacturers will have similar quality control programs that'll ensure consistency. So while it's not necessarily manufactured, if the material we bring in might not be manufactured to the American standard, there is a very similar Mexican standard that they are adhering to. That is a very, very close, like in that one that I showed, there is a Mexican standard that is nearly identical. If you translate and look at the two, they are nearly identical between the CPC 40 with limestone and the type 1 and the type 1L. So I think there are different standards between the countries, but there are close correlations, and I think the quality control would be very similar from a major cement manufacturer.
One additional comment on that to what Jason said is countries adopt ISO. And one thing to keep in mind is ISO and API co-brand each other. So ISO co-brands the API spec 10A. You got a different number on it. But what that means is any of these cements that come in from other countries, they've been made to ISO specifications. They have to meet the same specifications as the API.
Thank you.
Tessa?
Yeah. I don't know if my video is working right now, but question for you. And I think Todd knows where I'm going with this one because I've worked with Todd on IOGCC before. Have we seen much in way of comparison of regulatory approaches to these new classes of cement with European regulatory bodies as well in terms of that? I know we see a lot in terms of interstate comparisons, but as we pointed out, the tax changes as we go across country boundaries changed greatly. I didn't know if there had been any cooperation there to, use others' good ideas or approaches and see what has failed us in some of these, especially approaching new classes of old cements, as it were.
I'll take a first stab at that. Again, because of the API ISO work, there's pretty much identical on the standards, but when you start looking at where other countries are on this, Europe is actually quite a ways ahead of the United States on looking at specifying and coming up with some of these alternative blends. Have been for quite some time. Most of your European cements do have, some of them have up fit that didn't have it some time ago, have all got 15% or more limestone blended into them now, not even getting into some of the alternative materials they're using. So yeah, the United States is playing catch up on this in some regards.
Yeah, and I would add on that, is that when we launched the 1L product in the United States, in Canada, we launched this product in 2010, 11, and it actually launched earlier in Europe as well. So we already had all the data, all the testing and performance, and any concerns that we had in producing this product. We're not the first ones coming out with this product. The United States is actually a little bit behind the rest of the world in some capacity in this regard.
Any other questions? Okay, we've got one from Jason.
Hi there. I was curious if you could tell me what are the differences between Class A and Class L cement?
Jason, can you repeat the question a little louder?
I'm sorry, it's my microphone situation is less than ideal. Could you tell me what the differences are between Class A and Class L cement?
From Holcim, it's the utilization of the pozzolans and the limestone in the cement. I mean, it would James, I think you could take a better lead from API. I think that's more of the answer he's looking for.
Yeah, Class A does have limestone, or it's permissible to have up to a certain percentage. I believe it's 15% limestone interground in it as made. But the differences between K and L is designated more as a lighter weight cement, whereas A is meant to be more of a conventional high strength HSR cement, and the conventional density range is kind of the way they're written. But one thing to keep in mind though is these class K and L cements, the specification properties and performance properties of these cements are manufacturer specified. So API is not specifying those properties or the chemical. It's up to the manufacturers to specify and then manufacture to those specifications. Does that answer your question?
Yes, thank you.
Oh, we've got another one. Any? There you go, Danny. Danny, I have you unmuted from my side. I'll click it one time to mute you back and try to unmute you again. Just a moment. Okay, I'm going to ask you to unmute. Again, from my side, you're unmuted, but we can't hear you. Danny, if you want, you can maybe email the question and we could make sure you get it answered. I apologize, it just, we can't hear you. Any
This-
other questions? Oh,
This is Todd here. Yeah. We have had some questions come through the year and the panelists are aware of those, but I was interested in any just broad brushstrokes about like the percentage and usage and uptake of some of the alternate cement, additives and types and the processes, I guess, by which, and I'm talking about, we hear about things like the resin side and the alternative polymers, but I'm wondering if that's something you see, because of some of the pinch in the supply chains, times like that, you see those things coming to the fore at all, and just some general comments on that I would like. If anybody has any.
So I think I can answer this. The more niche ones, the resins and things like this, they're usually very application specific. They're usually used in cases where you cannot get a good seal, or if you're trying to repair a well and you're trying to repair and restore zonal isolation, and you can't get cement or a blend of cement and pozzolanic additives to do what you want it to do. You can't get it to penetrate a casing leak, or you can't actually get cement injected due to the particle size. That's when you're going to use these resins and things like this.
Dump baler applications. Dump baler applications.
Right, dump bailers and very, very small microannular squeezes, and squeezing leaking cement plugs and leaking bridge plugs, things like this is where you're going to see the resin, the use of resin. It's not really, it's in most cases it's going to be very, it's going to be cost prohibitive to an extreme to try to replace Portland or any of these other more common pozzolanic filler kind of materials with resin, just because of the extreme cost of resin.
Just to give some scope to that, the materials that we're talking about on a cost basis, a typical cement blend can be, say, for example, $100 a barrel, whereas a resin, you're looking at more $5,000 to $6,000 a barrel. That's the kind of extreme differences that you see with costs. And on the supply chain basis, resins are actually very hard, take a lot of lead time. If you're going to be pumping using anything other than a small amount, getting them is quite difficult now.
Thank you very much. I appreciate that.
And my team sees the same thing. It's on a case-by-case basis. It's typically used after a squeeze has been completed to shut off the microannuluses.
we've got a question from Clay. Clay,
Yeah, this is actually Danny. I walked down to Clay's office. I'm Director of Oil and Gas for Texas. Just curious, has there been any solubility tests that y'all know of that's been done with the 1L when exposed to corrosive fluids?
I can address that, or Jason, I see he's unmuted. You want to go first, Jason?
So I was going to say it's something we have started to look at in our labs. We have not really had a ton of time to complete any sort of in-depth study on the limestone cements when it comes to corrosive fluids. What we have seen, just the very broad strokes, is the very broad strokes of what we have seen is that the typical formation fluids you're going to see, they're not going to be exceptionally low pH where you're going to see these cements eroded away. I mean, for the most part, the lowest brine I think that I can recall seeing anytime recently is going to be like an acid mine drainage up in coal mines up in Pennsylvania, and even that is typically around a 4 to 5 pH, which really, from the very, very limited data we've seen in a handful of hours to a day of exposure, shows essentially no loss of weight on a standard density 14 to 15 pound per gallon type 1L cement.
There's a lot of confusion in the industry on this, generated by a lot of lab testing that, in my opinion, wasn't properly carried out. When you start doing corrosion testing on unconfined samples like cubes, you can get some erroneous results because they will start to spall as they expand. Where it's in a confined state, those samples wouldn't have performed like that. You expose any Portland-based cement, whether it's got pause, silica, limestone, any kind of filler like that, the weak link in any of them is the what's basically your unreacted porosity, your unreacted water, which creates porosity, and that's the mechanism by which corrosive fluids such as CO2, carbonic acid, can get into the cement. Now, what's not shown in a lot of this testing also is it causes the cement to swell. That swelling in an unconfined state is what causes that spalling and disintegration, whereas in a confined state, it improves your seal. It reduces the cement's relative permeability to water or gas. So to say categorically that Portland-based cements are susceptible to corrosion, yes, they are. But what is the results of that? That's what you want to be asking. Does it interfere, or does it cause a reduction in that zonal isolation? If you go back to some of the work, the CO2 injector fields in the Permian Basin, some work that was published by Sandia many years ago, it showed that no, that isolation is not hasn't been compromised. Where it can get compromised is if the metallurgy of the casing itself can't handle corrosion fluids. That's the weak link.
But if you have good cement, you don't have the corrosion of the casing, right?
Correct. Well, yeah, I mean, you got to have that uniform cement sheet. So if it's like anybody in this call knows, if you don't have a good cement job, your problems are fixing to start.
Yeah. Okay. Thank you.
All right, everybody, is there any more questions? Okay, so Todd, do you have any last comments?
No, just a big thanks to all the presenters in this panel today. We hope that everybody listening has had gotten some of the 30,000 foot view, digging down into it a little bit about cement and what it's about, and supply chains and issues and type classifications. We appreciate you coming today. And if you have any questions, the contact information, of course, is on the screen. Reach out. Feel free to reach out to us at IOGCC as well. And we look forward to seeing you again. Just a quick note to the regulatory folks here, by January 20th, if you can get the surveys in about this next year's ERT series, and we'd like to get that information in and start putting that together. So thank you very much, everyone.
1 second, this is Amy. We have one more question that popped in, if we can take that. It's Bob Brinkman. Bob?
Yes, thank you, Amy. With respect to the Portland cement that you guys are talking about, for, behind the casing in the annulus, either in surface or on down, or in P&A, there was one of the speakers was talking about not using limestone or calcium carbonate to fill voids. Well, that's a void. So I'm not sure if I'm missing something or exactly what the detail was on that. Thanks.
I think that was Jason.
I think I might misunderstand, or either I misunderstood your question or you misunderstood me. I mean, we absolutely are using calcium carbonate, and it has been used for a long time, blended and now underground with cement to take up space, to act as a filler in with Portland cement. I mean, is that what you were looking for? Or are you talking about the void space behind the casing that we're filling with cement? I guess I'm not quite sure.
Yeah, I think I got you. It's just, I thought you were saying, I understand that they mine limestone. That is what is used to goes through the kiln, the clinker, et cetera, to make the Portland cement. And there's different types of cements for well applications. Obviously, you're talking about K&L cement. I'm a hydrogeologist, so I'm not up on these like you guys are. I'm not a petroleum engineer. But anyway, I thought you were saying something about not using limestone to fill void space, but I think you just said that it is used. And so I guess my question is answered.
Yeah, so really, I mean, really the difference between the limestone that goes into Portland cement. So the limestone that goes into Portland cement to make it is run through the kiln, and it's essentially cooked through the kiln, then turned into clinker, and then reground with gypsum to make standard Portland cement, and up to 5% limestone to make standard class A or C or type 1 or type 3 cement. And now the difference for type 1L, let's say, is instead of intergrinding up to 5%, you're now allowed to intergrind up to 15% limestone after the Portland cement clinker has been manufactured. We're just adding more limestone on the back end to reduce the amount of Portland, reduce the amount of limestone that we're cooking and the amount of carbon dioxide we're driving off that limestone as we run it through the kiln for the simplest explanation.
Okay, I appreciate that. So it sounds like it's not so much a function of how it is when it's placed behind the casing, but more related to other issues. It's not a
Well,
Go ahead.
Right. So that's the driver, I think Bill touched on this, the driver behind making the Type 1L and the limestone extended cements is to, reduce the amount of CO2 released into the atmosphere. The big driver in releasing CO2 is the energy used to heat the limestone to drive the carbon dioxide off. So you think about it, you've got CaCO3, calcium carbonate, you've got to drive a CO2 off of each molecule of calcium carbonate to make the clinker. So it takes energy from fuel to do that. And then you've got that CO2 you're releasing as well. So we're just trying to, really they're just reducing the amount of CO2 from both fuel burn and, removing that carbon dioxide from the carbonate.
Yeah, it's about carbon footprint. It's not about well performance, cementing performance. Okay, thank you for that explanation.
Todd, I've got one additional comment I wanted to interject here. It's something we've been dancing around for the past hour and a half, but I don't think anybody has just come out and stated it. Particularly in the United States, when you're talking about ASTM Type 1 and API Class A, they're interchangeable. For most of the cement mills that products that sources I've seen. And the same thing can be said with ASTM Type 3 and API Class C. So they're interchangeable. If you pull up the specs on both of them, on the chemical specs, the only difference is if something's being sold as a Type 3, it hasn't been subjected to hasn't necessarily been subjected to the API performance test, which is easy to do, and the cement pumping company is going to do that anyway before they can use it. So there's a lot of equivalencies there that you can take advantage of.
That's great. That's helpful, James. Thank you. Open it up one more time to any more questions. Give it a second here. If anybody has anything else, please raise your hand. Okay, well, with that, again, my thanks on behalf of IOGCC and the RRT committee, and we look forward to seeing you again in future webinars, and we wish you all a good day.
Thank you.